Hi everyone, welcome back. In this video we are going to model a compression spring with a variable pitch in SolidWorks. Once the geometry is completed, we will perform a nonlinear static analysis by applying a prescribed displacement, axial displacement. From the reaction forces, we will calculate the stiffness of the spring and examine the stresses produced during the compression. Okay, so let's start by creating a sketch. Top plane, create a circle that is going to represent the mean coil diameter. For our case is 10 millimeters. And then we are going to go to features, helix and spiral. You can choose height and revolution or pitch and revolution. You can have a constant pitch or a variable pitch. And you can reverse the direction if you want, clockwise, counterclockwise. For our case, this is a variable because the compression springs start by a low and then high pitch. So let's start by 0.5. This is pitch and revolution, defined by pitch and revolution. And then we go 1.5 millimeter pitch and 0.5. So you go half a revolution with this pitch, and then 3 millimeters. Now you have completed one revolution. We keep the pitch 3 millimeters and we go 6.5 more, and then you go again 1.5 and you go a half more revolution, so it's 7 and 0.5 and a half more, 7.5. So it starts a little bit low and a higher pitch and low again. And then you go features, sweep boss base, circular pitch or profile, circular profile. And then you define the wire diameter 1 millimeters. And now we can create two parts, up and down here. But first we want to cut the surface. So you choose the top plane, you go to surface, cut with surface, and cut below. And do the same thing. But first we need to create a plane here. Let me just choose this, choose the plane and choose this point. And now change the direction for the arrow and cut the upper part. Now we can hide this plane, hide this. And now we can create the parts, sketch, and this should be a square. make it reverse the direction 1.5. And we can mirror this or do the same process one more time. 15, right? Yeah. And then make these two equal to each other. And then extrude 1.5. Now the geometry is completed. We can apply some material, edit material, apply alloy steel, apply and close. Now we can go ahead to simulation, new study, create a nonlinear static study, because we are going to have a large displacement here. We fix this part and apply a displacement, axial displacement on the top. Advanced features, choose this, flat on surface, and let's apply some 7 millimeters, and the direction is correct. Right. We are going to compress this. The distance here is 19 or 20 millimeters ish. Now we are going to mesh and run the study. The material is applied, right? Linear elastic. It should be plasticity. One misses plasticity, and yeah. Let's mesh and run with the automatic auto mesh. Okay, so after 5 minutes or so, the simulation is completed, and you can see the nonlinear simulation is done in 13 steps. The last step is the 7 millimeter compression state, and you can see here by plot tools, probe, you can see that you have here a little bit more stress than here. Orange is, yeah, you can see 500 something, this is 400 something. You can choose ISO clipping or mesh section if you want, and you can see a more clearer stress distribution for the spring here. When we are talking about springs, the inner part of the spring is have more stresses and heats up, especially when we are talking about fatigue. Mesh section, ISO clipping, you can play around, drag this tool and see for yourself that the maximum stresses are inside the spring. And yes, you can maybe go to results, check the forces for this. Can we hide the bodies here? Or maybe just choose this part and update, and you can see the reaction forces. It's 10 Newton, and you divide the force to get the stiffness. Stiffness is Newton divided by millimeters, so this force divided by 7 millimeters that we applied, then you get the stiffness for the spring. So yeah, this is how you apply do a nonlinear analysis on a spring. Like and subscribe if you learned something. Thank you.